Okay.
In lecture 2, we are going to study how to obtain the spectrum shape and the physical properties of the materials related to the optical properties. So first, let's review the propagation equation. So what we studied in the last lecture, when the light propagates in the materials, we could obtain the propagation equation, which was in one-dimensional case. D2 upon dz2 minus 2 0 d2p and then dt2. So as we studied, the left side, left arm is simply a wave equation. In this case, the electric field is propagating in the z direction with a speed of c. And on the right arm, you could see the polarization change in time, and then which is a source of polarization. So what we are thinking about is, so if we have a material, the light oscillate, so E field oscillate, and then propagating in a z direction. And this material, due to the electric field oscillation, similarly, the material is affected by this electric field oscillation, which gives a polarization change in time, which is a source of polarization, and this polarization affects the wave light propagation, and also this light field also affects the materials. So as I talked about, the wave equation itself is already kind of one of the most famous partial differential equation representing the wave, and there's not much change for the light itself. However, the polarization inside material, this depends on the material. So depending on the materials, this term could be varied. That's why how to estimate the P is a key point. So there are several methods how to estimate the polarization inside the materials, and depending on the theory, I can categorize somehow like this. So P can be estimated from quantum mechanics, which is a semi-classical way of the analysis. And if you estimate the P based on the electromagnetics, it's called a classical theory. So in this lecture, we're just going through by using the classical theory to understand the spectrum shape and material properties. Okay. So now what? As a next step, we are going to change the propagation equation in the Fourier domain. So Fourier domain is the way it is. So we are just thinking about the electric field oscillation and propagation in time. So this is a real space. But in many cases of the spectroscopy, such as absorption spectrum or vibrational spectrum, we are thinking about this oscillation field with like in a frequency. So it's omega or f, omega or hertz, and intensity. Right. So we can see that some sort of the absorption spectrum or vibrational spectrum. So in many cases, it is very useful if you consider the equation in the frequency domain. So to change the real-time domain to the frequency domain, just simply you can use the transform of the response to the frequency response by using Fourier transform. So let's think about first in the one-dimensional case. Let's start from the one-dimensional case. So again, in the one-dimensional case, d2 d minus c squared zero d2 d2. Okay. So how to obtain the equation in the Fourier domain is just simply the left term and right term is we apply the Fourier transform for example electric field and polarization change in time to the frequency response of electric field and polarization. And then, as I mentioned, by changing this equation in Fourier domain, we can think about materials response and consider in a spectroscopic space. And also the other important things is calculation for the temporal derivative is much easier, because if you have a function of f of t and then partial differential of f is in the Fourier domain, you can just simply this term can be changed to the I omega times f. So it's very this partial derivative of t can be eliminated. So if you write this propagation equation in the Fourier domain, let's just change to is changed to the omega. not t, plus since the partial derivative of t is changed to the simple simply I omega, and I omega is squared, and it's changed to like this, the omega equal, and this partial derivative, second derivative of p also can be changed to mu 0 minus is coming from the square of I, and omega squared p g omega. Okay. So as you can see from this, originally this equation, propagation equation, was partial differential equation, which is mostly quite difficult to solve, even for a very simple form like this. And actually, most of the partial differential equation like this one, you cannot solve analytically. So, but in this equation, since the derivative of t is changed into just the normal type of the parameter, it's just a change to the differential equation of z, so propagation direction. So it can be solved much easier.